So hi everyone. Today we'll be starting our seventh tutorial class. So uh, Today we'll basically continue our discussion on the rotation and partition function. But before coming to that, let me briefly revise the things that we've discussed in our last class. So, so, uh, so we started our last class by discussing about the rest of the thermodynamic quantities in terms of like by expressing the thermodynamic quantities in terms of the molecular part, in terms of molecular as well as canonical partition functions. So let me just revisit the things once again. So we know the internal energy. The internal energy is related with the molecular partition function. It looks like this: internal energy U equal to U0 minus 1 by Q del Q del beta at constant volume, or you can write it like this: U equal to U0 Q minus U0 equal to minus delta ln Q by del beta at constant volume. So this is the expression of the internal energy. We have derived this before, and the pressure expression also we have derived, right? The pressure P equal to KT delta of ln Q by delta V at constant temperature. So these two thermodynamic potential expression we have already derived, but using these two expression, we will basically we actually had basically derived the expression of the first thermodynamic quantity, that is the enthalpy. Okay, the enthalpy. So enthalpy is basically denoted by H, which is related by other thermodynamic potentials by this relation H equal to U plus PV. Now from here, as you know, you already know, here there are a lot of familiar terms are there. One is the internal energy, and next is the pressure. So you can, as you can write the internal energy and pressure in terms of Q, that is the canonical partition function. So that means we can also write the enthalpy in terms of Q, right? So H minus H0 we can write like minus delta ln Q by delta beta at constant volume plus KTV delta ln Q by delta V at constant temperature. This is the basic expression of the enthalpy. You can further simplify it, okay, or you can just keep it like this also. This is basically the expression. Next thing that we have calculated, we like verify what will be for a monoatomic ideal gas, what will be the expression of the enthalpy, right? So for monoatomic ideal gas, so for a monoatomic ideal gas, so monoatomic means there is just one atom is there. So in 3D the degrees of freedom will be 3. So that means we can consider that gas, each of the particles of the gas can be a particle that is trapped inside a 3D box, right? So this will help us to assume its rotation translational partition function, okay? And that expression we have already derived in our previous classes. Okay. So for a monoatomic ideal gas, we consider it as a non-interacting. So we take Q equal to Q to the power n by n factorial. Okay. Now by taking the Q as Q, where Q is small q is the molecular partition function. Okay. and we are considering the case where the particles are non-interacting. So that's why we basically divide the q to the power n by n factorial. Otherwise, if they are interacting, then q would be simply become q equal to capital Q equal to small q to the power n in case of interact. Here it's non-interacting. So for this case, we have just substitute the expression of capital Q in the expression of the enthalpy, delta beta of q to the power n by n factorial. Similarly, KTV delta of ln q to the power n by n factorial by delta v at constant t. Now, after doing this whole derivation, we got the expression of enthalpy. Looks like this: 5 by 2 NKT. Okay. So NKT, you can further simplify this NKT, right? N is the number of particles in the box. So if there are a small n number of small n moles of particles is there, then the capital N would be n into Na, where Na is the Avogadro number, right? That means H minus H0 would be 5 by 2 n into Na K T. Na into K is simply is the ideal gas constant, which is R, n into RT, right? So this is the H minus H, this is the value of enthalpy we got. Now we find out that, like, for an ideal gas, if you already knew the expression of its from its expression of thermodynamic potentials, from here also if you evaluate the expression of enthalpy, it looks like for an ideal gas we know the internal energy in 3D is 3 by 2 nRT plus PV, we know it's nRT for an ideal gas. If you substitute PV equal to nRT is here, that means enthalpy is 5 by 2 nRT. That is just by using normal kinetic theory of gases, you are getting the value of enthalpy as 5 by 2 nRT, which is exactly similar to the enthalpy that we got using the statistical point of view. So that means whatever we have derived, the expression of enthalpy is consistent with thermodynamic models, right? Similarly, you can, if you know the enthalpy, you can calculate the specific heat at constant pressure. Cp is nothing but del H del T at constant pressure. Okay, these are some things. These are basically the importance of enthalpy, importance of calculating the enthalpy. From there, you can calculate the other quantities, like here, the specific heat at constant pressure, right? So after that, we do some problems. Next, a very important quantity that we have discussed is the Gibbs free energy. Okay. So Gibbs free energy. So Gibbs free energy is basically a very important quantity in, when you want to know whether a process is spontaneous or non-spontaneous. You have to first check whether this Gibbs free energy at constant pressure and temperature is less than 0 or not. Okay, so if delta G for a process is less than 0 at constant temperature and pressure, so that means the process is spontaneous. Okay, it can basically occur by its own, that means. Okay, so in this perspective, Gibbs free energy is a very important thermodynamic quantity to evaluate for a process. And so in order to write the Gibbs free energy in terms of the canonical partition function, we have actually used this same way that we have done with the enthalpy. So here also you first write the Gibbs free energy in terms of thermodynamic potential, G equal to H minus Ts, then H we already know U plus PV, then the expression will become U minus Ts plus PV. Okay, This is the expression of the Gibbs free energy. Now from here we have done the same thing. Uh, so H, so U minus Ts is nothing but the Helmholtz free energy, right? U minus Ts. And in the previous lecture, we actually derived the expression of the Helmholtz free energy, which is nothing but this: U minus A is equal to minus KT ln Q. Okay. So now, if you simply substitute the expression of the Helmholtz free energy here in the Gibbs function, then you'll be getting G minus G0 equal to A minus A0 plus PV. So that means minus KT ln Q plus PV. So this would be the expression of the Gibbs free energy. Okay. Now here PV, for an ideal gas you can put PV equal to nRT, right? That means G minus G0 for an ideal gas, you can write KT ln Q plus nRT for ideal gas. Okay. So we have done some problems related to this. And lastly, we have started a new thing that is called a rotational rotational contribution to the partition function. So as we have discussed, the energy of a molecule, okay, rotational partition function. So what happens here actually? The energy of the energy of a molecule is divided into different modes. So let's suppose for a jth molecule, the energy Ej depends upon first the translational part, second is the rotational part, third is the vibrational part, and fourth is the electronic part. So these are basically the four energy contribution that comes inside the energy of a molecule. Now, so in the previous discussions, we only considered the translational part of the energy, okay, of a molecule, but we did not consider the other parts, the rotational, vibrational, electronic part. The reason is because at low temperature or at room temperature, the translational partition function is only the dominating part in the energy of a molecule. The rotational, vibrational, electronic parts will only become significant when you high the energy. Okay, and at that high temperature or at high energy, then the rotational, vibrational, electronics contribution will come, and their order is also like this: the more high energy, the more electronic. The first you will get rotational, then you will get vibrational, and then you will get the electronic. Okay, this is the scale of the energy scale of each of the contribution. First comes the translational, then comes the rotational, then comes the vibrational, and at the last the electronic. Now you can write then the partition function. If you consider the whole energy, then you can write the partition function like this: Ej translational plus Ej rotational plus Ej vibrational plus Ej electronic, right? Now that means you can write the partition function Q as Q2 Qt into Qr into Qv into Qe. T is the translational, rotational, vibrational, electronic part. Okay. Now okay, so these are the different parts. Okay. Now, okay, so now we in the last lecture we have discussed some about the rotational part. Okay. So the rotational part looks like this. So first, let me write the rotational energy level. So from the atomic molecular part, you already know from the spectroscopy part also. You can know the energy, the rotational energy levels of a molecule looks like this. The expression of the energy looks like this: Ej equal to hcb. It is the rotational constant J into J plus 1. But J are the different rotational levels. J equal to 0, 1, 2, dot, dot, dot. So it's like these are some energy levels which are quantified by J. J equal to 0, 1, 2, 3, like this. And these are the energy that is associated with the jth energy level. Okay. B is the rotational constant. And I is the uh, moment of inertia for linear. In the case of a linear system, the moment of inertia will be looks like this: linear molecule. R is the bond length. Now, what we did, we have simply then we want to basically, our objective is to find the expression of the rotational partition function, right? So to do that, what we have done, in the expression of the rotational partition function, which looks like this, gj equal to e to the power beta ej. So we put this expression of ej in this expression of the rotational partition function, and gj is the basically the degeneracy. There are actually, these states are basically degenerate states. For a jth state, the degeneracy would be 2j plus 1. Okay, so 2j plus 1 e to the power beta hcb j into j plus 1. Now, yeah, so if you just substitute the summation in terms of integration, it would be looks like 2j plus 1, it will be power beta hcb j into j plus 1 dj. If you do the whole integration, we will be getting qr equal to 1 by beta hcb. So this simplification that we have done right now, there is a limitation. This simplification is only true when the temperature will be higher. High temperature means the temperature with respect to a certain certain cutoff temperature or certain level temperature. So we basically, just like the just like the case here also, we have to define a reference temperature. Okay. So we are telling that reference temperature as theta r, which is known as the rotational temperature. Okay. So when the temperature of your system, that is T, is greater than equal to the theta, that is the rotational temperature, then only this approximation is valid. Okay. So we can define theta as hcb by k. So we can write qr equal to 1 by k, 1 by kt, right? So hcb by kt, this would be kt by hcb. So we can write t equal to theta. Okay, this would be the expression of the rotational partition function, given the fact that the temperature of the system is much higher than the rotational temperature. So, and all this approximation, that like all this derivation approximation that we have done, is only applicable for linear systems. If it is non-linear or something like that, then we have to use some different approach in order to get the expression of the rotational partition function. Or other way, we have to do the whole summation of each energy levels. So, so these are the things that we basically discuss in our last class. Okay. Now for today's class, Okay, so actually missed one thing, one key important thing. So, so let me, there is a symmetry factor is involved in the expression of the symmetry number, sorry, which is involved in the expression of QR. So the modified QR by including the symmetry number looks like this: H equal to sigma by HCB, or T by sigma into theta. Okay. Now here sigma is the symmetry number. Okay. Symmetry number. Okay. Now, what is the significance of a symmetry number for heteronuclear molecules? Sigma is 1. Nuclear means the atoms that constitute the molecules are basically will be different species. Okay, like H2O or CH3, okay, like this. NO. But you can see the molecules are the atoms inside the molecules are basically different species. For homonuclear, however, homonuclear means obviously the opposite where the atoms are similar. Sigma is 2, like O2, H2, something like this. The atoms are similar species. So homonuclear case, the sigma symmetry factor number is equal to 2. Okay. So now the next thing that we wanted to do, basically, we want to solve some problem regarding this. But before solving the problem, what we have to do, we have to write this QR, the rotational partition function, uh, as a function of the known parameters. Okay, so um, here the known parameters means one of the thing is the B, what is that is known as the rotational constant. So B has an expression, is a big expression like this: h cut by 4 pi c into I. I is the moment of inertia, that is mu r square. Okay. Now here, so here now if you substitute the expression of B in the expression of the rotational partition function, it looks like this: h equal to sigma HCB. Now here KT will be sigma HC. Sorry, if you substitute H, it will, H card would be H by 4 pi, H by 2 pi. So if you substitute that also inside in the expression of B, then the expression will become sigma H square KT mu r square. There will be 2 pi multiply 4 pi, become 8 pi square, right? This would be the expression of the rotational partition function. Now here basically uh, mu r square. So mu r square coming from the fact that it's a I equal to, consider mu r square as it's linear, and mu is basically the reduced mass. M1 into M2 by M1 plus M2. So M1, M2 are basically the mass of the mass of the atoms in the molecule. Okay. So now let's do some problem. So first problem is problem 1. Is for the N2 nitrogen. You have to find uh, we have to find the rotational partition function for nitrogen. So the question is the NN bond length R is given 109.76 picometer for nitrogen. Then now using the high temperature approximation, using the high calculate the QR, sorry, the QR at T equal to 300 Kelvin. Okay. Now here, so we know the expression of the Q rotational, right? So Q, sorry. So QR looks like this: 8 pi square by 80 by sigma x square, where I is mu r square is the moment of inertia, and mu is simply m1 into m2 divided by m1 plus m2. Now, so this is the expression of the rotational partition function. Now here, the things that you know, uh, first is you can evaluate the moment of inertia thing, right? So in order to calculate the moment of inertia, you have to have the expression, you have to have the value of the reduced mass mu. So here, so for the, it's a homonuclear, so both are the nitrogen atom. So the mass of the nitrogen atom is, we have to first write the mass of the nitrogen atom is 40.0067 U, and one U is missing, and 1.66 into 10 to the power minus 27 kg, right? Now, so that means Mn would be, if you multiply the mass with 1.66 to 10 to the minus 27, the value of U, you will be getting 2.325 into 10 to the power minus 26 kg. Okay, this will be the mass of nitrogen. Now, after getting the mass of my nitrogen, you can easily calculate this reduced mass, which will be equal to m square, as both the mass are equal, mn square by 2mn, which gives mn by 2. So now, okay, so we got the mu. Now, after getting the mu, you can calculate the moment of inertia. So we need the bond length, right? So bond length is R equal to 109.76 picometer. Okay. Now, as we are dealing with the SI unit, so you have to convert the unit from picometer to meter, right? So pico 1 picometer is basically 10 to the minus 12 meters. So 109.76 into 10 to the minus 12 meter. So 1.097 into 10 to the minus 10 meter. Okay, this is the bond length. Now, as you got the both the reduced mass as well as the bond length, now the task is to calculate the moment of inertia I, that is equal to mu into r square, where mu equal to mn by 2. So mn by 2, so that means 2.325 into 10 to the power minus 26. You have to divide this thing by 2, multiplied with the bond length 1.097 into 10 to the power minus 10 whole square, mu by 2 r square. So you will be getting I equal to 1.40101. This is the value of the moment of inertia. Sorry, this is a 10 minus 46. Sorry. So I would be 1.40 into 10 to the power minus 46 kg per meter cube. Okay. Now I'm going to copy this thing. Now in this expression, what we have to do, we have to substitute the values here actually. So QR is basically, first is I square constant. I have calculated just now 1.40 into 10 to the power minus 46. K is the Boltzmann constant, 1.38 into 10 to the power minus 23. Temperature is given, that is 300 Kelvin. This whole thing divided by, as we are dealing with a homonuclear molecule, that means both the atoms inside the molecules are basically identical. So that means the sigma value or the symmetric number would become 1, right? Oh, sorry, 2, right? So sigma is 2, homonuclear. So 2 into h square, the h is the Planck's constant value, 6.626 into 10 to the power minus 34 whole square, right? So QR will be getting almost similar to 5.22 into 10 to the power 1. The value of QR would be that is that means around 50, right? So at 300 Kelvin there is like 50 states that are available for rotational modes, right? Only 50 states are available. So that means you can see at room temperature the contribution that comes from the rotational rotational energy levels are very less. Only 50 states are there, right? So that's why we only consider the rotational energy states when the temperature reaches a very high value. If we made the T higher, you can see QR is very proportional to T. That means if you make T higher and higher, that means you'll be getting better accessibility to the higher energy states. Okay. Now we'll be discuss another problem, second problem, and this problem consider HCl, the hydrogen chloride. Okay, so the HCl bond length is given by R, that is equal to 127.45 picometer. Now we have to calculate the Q naught of HCl at temperature equal to 300 Kelvin, right? Now here, so a similar way, similar strategy also here also will be followed. So the first thing is write the masses, and from there calculate the reduced mass, and lastly the moment of inertia. So hydrogen mass is 1.00784, chlorine mass is 35.453 u. So the reduced mass mu would be mH into mCl plus mH plus mCl. Okay. So this would be the expression of the reduced mass of both. So now, we have to substitute the mass of hydrogen and chlorine gas. So in that case, we will become 1.67 to 10 to the power minus 27 into 5.366 into 10 to the power minus 26 divided by 1.67 into 10 to the power minus 27 plus 5.366 into 10 to the power minus 26. So the end value would be 1.62 into 10 to the power minus, it's fine, 1.62 10 to the power minus 27 kg. The reduced mass, right? Now from the reduced mass, you can calculate the bond length. The R is given. So I equal to mu into R square, mu already know 1.62 into 10 to the power minus 27. And R square is a bond length that you already know, 127.45 whole square. Now from here, if you calculate the things, you'll be getting I equal to 2.6233 into 10 to the power minus 47 kg meter square. This would be the expression of value of the moment of inertia. So got the moment of inertia expression. Now we have to just simply, other information is already supplied in the problem, so we can write the rotational. Q rot equal to 8 pi into plus 1 plus 6 10 to the power minus 47 minus 23. Guess the Boltzmann included 10 to the 300. The whole thing is divided by 1 into h square. If you calculate this, the rotational will be coming as 19.6 meter, which is very less actually. The rotational level. So these are the problems that we have discussed now. So let me just revisit the problem once again. How to do. So in the expression of the rotational partition function, which is basically given by these ideas. Okay, so So we have started with by evaluating the reduced mass mu. So if the mass of the this nitrogen atom is given from there, we can first calculate the reduced mass, that is a mu, right? And because in the expression of QR there is I is already there, so from mu we calculate the I, then it is fine theta of sigma. The sigma is here the symmetry number, okay. Like for the previous problem, for water nuclear phase, the sigma was 1. I got the I value. Now if substitute the I, the amount of inertia into the main expression of QR. From there you will get um, both the values, right? So, uh, so far we have only discussed about the linear temperature contribution, the rotational, rotational partition function. Okay. So till now we discussed the linear case. Now we'll discuss the non-linear case. Okay. Let me write. At height. Okay. So now you can write the rotational partition function QR equal to 1 by sigma KT by HC equal to the power 3 by 2 by pi into ABC. The proof is actually beyond the scope of this lecture. Okay. So anyway, if you do the calculation, you would be end up with this kind of rotational partition function. Okay. Now here ABC are constant. Uh, so here what is ABC? ABC are basically, now this value of ABC is, there is no such formula using which you can calculate the value of ABC. So basically, uh, ABC values will be supplied into the problem. Okay, this rotational constant value there. Now we will check what will be the cases under which this approximation will be good. Okay. So we will first do some problems. Okay. So problem 1, water H2O. Okay. So in this problem, the rotational constants are given. So the rotational constants of water are 27.877 centimeter inverse, P equal to 14.512 centimeter inverse equal to 9.485 centimeter inverse. So we got the value of B and C, A, B and C. Now simply have to substitute all this expression into the expression of this rotational partition function. So so for asymmetry, let me just write the formula once again. For asymmetric so at high temperature, the expression of the molecular partition function, rotational partition function QR would be simply looks like this: 1 by sigma AP by HC C by 2 pi ABC 1 by 3. So here the T is 300 Kelvin. The ABC, the multiplication of ABC will become 27.877 into 14.1512 into 9.285. The ABC would be 3759.2 picometer. Okay. Now if you substitute the temperature, the rotational constant and all into the expression of the rotational partition function, then we will be getting QR equal to 1.0270 by sigma T will not 300 Kelvin, sorry 298 Kelvin divided by K divided by ABC per centimeter cube to the power half. Okay, now if you substitute all the parameters that are supplying the problem, T equal to 298 Kelvin, sigma equal to 2, as this is a heteronuclear H2O. So we will be using sigma equal to 2. Now that means our rotational partition FQR would be 1.270 by 251.48 by 61.33. If you do the calculations, you will get 43.1. This is the This is the expression of the rotational partition function for this problem. Okay. So in this problem actually it's a 3D case where the all the rotational of constants are given, temperature is also given. Now we have to go basically step by step with the calculation, numerical calculation. Now we'll discuss another problem, the problem 2. Okay. Consider a gas of n identical particles with the canonical partition function. So Q and B is the partition function is beta. B means beta is basically given by this 1 by n factorial into 2 pi n by beta square by 3 n by 2 b minus bb to the power n exponential beta a n square b into exponential beta c n square v square b square. Now the question is, this ABC is constant. Derive the equation state. So ABC is constant. So first what we will do, so the partition function is canonical is given basically from here basically calculate the equation of state. So for that the first thing that we will do, we will write this partition function in terms of log, because you can see there are a lot of powers are involved to the power things. So in order to eliminate that and to make the equations are more simple, we are basically take a log. Okay. So log q. So if you take the log in both sides, log q equal to some constant, let's suppose it's k, or yeah, k plus n into ln b minus nb. Okay. Minus beta a n square b minus beta c n cube b square. Okay. This is the expression of the ln q, the partition. Now if you want to now if you want to derive the expression of the pressure, right? So as you all know that pressure is pressure thermodynamically related with the other potentials also. And in our last class, right, we have derived how the pressure is dependent upon the non-Q, log of Q. Okay, Q is the partition function of the ensemble. Okay. So ln Q can write ln Q equal to ln Q already I have right. Okay. Now, so what we will do? We will do the derivative because pressure expression is P equal to kT delta ln Q by delta kT, sorry, delta V at constant temperature and number of particles. Now, so you have already knew the ln Q, right? Just you have to substitute here. Okay, ln Q, that means so del V of ln Q. Del V of ln Q equal to first term would be del V of n into ln V minus nV minus del V of beta A n square V minus del V of beta C n by V square. So now it will become delta ln Q by del V equal to del V of n into minus, so gives you n by V minus nB minus, if you do the derivative with respect to V on this, then it will simply become minus will become plus. It will become beta A n square V square. Lastly is the beta C n cube V square. So now in this case del V of this would give you simply minus of minus, it will become plus of 2 beta C into n cube by V cube, right? Because we are doing the derivative with respect to V, right? So V cube, V square will become V cube, and a factor of 2 will be basically coming out. So that means we got the whole expression of the delta ln Q by delta V. Okay. So now what we have to do is now we have to just equal to, already know, kT ln Q by 2 P dot delta. Now let's substitute this thing here, then you will get some kind of a equation of state for this kind of a gas. So P equal to simply kT by n into n by V minus nV plus A by n square by V square plus 2C n cube by V cube. This is basically the expression of the pressure. This is basically the gas equations also, gas equation of state. Okay. This is how we can calculate the equation of state. Okay. So what I have done, that in the problem, what is mentioned, so in the problem, the partition, the canonical partition function of a system, that of a gas basically, that consists of an identical particles are supplied in the problem. Now given the fact that the ABC inside this partition, inside this Q, that they are constants basically, we have to derive the equation of state. Okay. So equation of state we like it is some p equal to something, right? The equation state of an ideal gas or real gas, you can write p equal to some function of volume, temperature, etc., right? So here also we know the expression of the pressure, right? If you somehow express that express the pressure in terms of other thermodynamic potential, then from there we can write the equation of state, right? So first what I have done, first to write this is the expression of pressure in terms of partition function. What we do, we require ln q, so first we calculate the ln q, then we do the derivative with respect to volume. After doing that, this is the terms that are remaining terms, and after substituting this delta ln q and delta vt into the expression of the pressure, I am getting this gas equation of state of it. So this is the way that you can do this kind of problem. So we have done a problem on, first we have done a problem on rotational partition function for a non-linear rotor, right? Where there are two A, B, C, basically three values of rotational constants are there for 3D cases. For that, we have calculated the QR, which is basically this nominal amount of energy level. Like for this very low temperature, like almost room temperature, is not able to push the system towards higher or more numbers of rotational energy levels. Anyway, so this one problem we have done. Next we have uh, derive the equation of state for a particular gas. If you know its partition function, canonical partition function, from there you can easily derive the gas equation of state. Okay. Now we will do another problem. So problem will do. Problem is uh, spin one particle. That means it can have spin -1, 0 to +1, right? Spin one particles placed in uniform. This is to be clear that this problem is not particularly related with the rotational partition function. This is in general problem. Okay. Placed in uniform magnetic field. Dz the energy levels are given by basically E equal to -m h mu by b0. So these are the basically the energy levels. Okay. Now the things that you have been asked to calculate. The first is write down the partition function. Rule 2 is the derive expression for average energy. Partition function is Q, average energy is angular bracket E, and lastly you have to find out find the limiting behavior of P at high temperature that means beta tends to uh, 0 and at low temperature that means beta tends to 0. So for these three are the problems. So now what you have to do, so the three energy levels, the E basically the E energy levels E1, E0 and E plus 1, E0 and E minus 1. So the energy levels would be M would be the values plus 1, 0 and minus 1, right? Okay, so because it's a spin half particles, right? So those are possible combinations are M equal to minus 1, 0 and plus 1. So the energy levels are basically this three would be the energy levels. Negative would be minus H nu Bz E minus 1. E0 would be 0 and E plus 1 would be plus H nu Bz. So these three are the possible energy states. Okay. E plus 1, this is E0, and this is E minus 1. Sorry, this is E minus 1, this is E plus 1. These are the three energy states are there. Now what we have to do, we have to find out first the partition function, right? As you know the energy of the system, from there it's easy to calculate the partition function, right? So first thing first, first thing we'll derive the partition function, okay? So Q would be summation over j to the power minus beta ej. So here there are three states are possible. So first will be beta e1, beta e0, beta e minus 1. If you substitute the values, it will become e to the power minus beta h nu bz plus 0 plus e to the power minus beta h nu bz. Okay, the expression of q looks like this. Now q1 plus, so now we know this thing to the power beta h nu bz plus e to the power minus beta h nu bz. So now we can write this thing in a more compact form. Okay, we know the how cos hyperbolic function is related to the exponential. So cos hyperbolic beta h nu bz, you can write it like this: e to the power beta h nu bz plus e to the minus beta h nu bz by 2, right? Cos hyperbolic function. Now if you substitute this thing here, then the q expression will become 1 plus 2 into cos hyperbolic beta h nu bz, right? So this is the expression of q, the molecular partition function q. Now from here, the first thing that we can calculate is the average energy, right? So the average energy is the first quantity, average energy. So the expression of the average energy looks like this. The average energy, E inside the angular bracket, looks like del beta of ln q, right? Now Okay. So this can be then minus ln q, you can write it as 1 by q into delta q by delta beta, right? So now delta q by delta beta, how can you write this thing? So q is already there, this is the expression of the q. Let me just copy it here also. Mm. Now in the top of it, if you do that derivative, delta q by delta beta, this gives you 2h cut nu bz into sine hyperbolic beta h nu bz, the whole in the denominator it would be 1 plus 2 into cos hyperbolic beta h nu bz, right? So this is the expression of, sorry, this is the expression, no, sorry, this is the expression of, yeah, this is the expression of del q del beta. Okay, now we need average energy, right? So for average energy, just substitute this del q del beta in the expression of the average energy, or also you know the expression of q. So the average energy E would be simply minus 1 by q is 1 plus 2 cos hyperbolic beta h nu bz, this whole thing into 2 h cut nu 2 h cut nu bz sine hyperbolic beta h nu bz. Okay. Now the average energy would be, looks like, minus 2h cut nu bz sine hyperbolic beta h cut nu bz by 1 plus 2 cos hyperbolic beta h cut nu bz. Okay. So this would be the expression of the average energy. Okay, this is the basically expression of the average energy for the system. Okay. Now what we can do next is so that we derive the first two problems are basically done. The calculation of the partition function is done. The derivation of average energy is done. Then we have to estimate. We have to basically see the limiting case. What is the value of the average energy at limiting case at both high temperature and low temperature. So to do that, we will take the limit beta tends to 0 and beta tends to infinite. Okay. So at I sorry at high temperature, that means beta tends to 0, the sine hyperbolic x would become almost close to x, and cos hyperbolic x equal to 1. So if this is the case for the high temperature, then the average energy would become simply 2h squared mu Vz into beta h squared mu Vz. This whole thing is divided by 1 plus 2. So because cos hyperbolic x tends to 1, so that means it will be 1 sine hyperbolic x. That means the beta h nu by Bz is basically x here. So x is basically beta h nu by Bz, right? So now, so that means it will become minus 2 by 3 beta h squared nu by Bz. So E is basically proportional to 1 by t, right? So if t tends to infinite, right, it's or tends to be, so if t tends to infinite, beta tends to 0, so delta E also tends to 0 linearly in 1 by 2. Okay. Similar way, it can be also calculated for the case of the low temperature limit of room. So now we will briefly discuss about the vibrational energy of the system. So okay, so for a vibrational, it's like It's the energy scale is like much more lower compared to the translation rotational. So it will only be prominent when the temperature of the system becomes much more higher than the room temperature. So still we look into it. Okay, so let's write the vibration. So the molecules, when you raise the temperature of a polyatomic molecule, so what happens? The molecules basically there is some internal there is some constraint bonds are there. So basically, although there are bonds, these constant bonds are there, but still at high energy, because the molecules energy become atoms inside the molecules inside the molecules also become very high energetic. That's why they are basically show this kind of vibration type of motion. Okay. So this the number of vibrational modes would simply be related with its degrees of freedom, definitely. Right. So let's suppose for a linear case, okay. So if the if there is if it is its n atomic molecule, so that means there are n numbers of atoms are there molecule, and if the case one is the molecule is linear, in that case the vibrational modes are equal to 3n minus 5. Second case, if the molecule is non-linear, it's not linear, then the vibrational modes would be 3n minus 6. Okay. So now now the thing is, each vibrational modes has actually its own partition function. Like each vibrational modes, you can associate it with its own independent partition function. So uh, so uh, so that means in a polyatomic molecule, each normal mode has its own partition function. Okay. So Q nu basically equal to Q nu 1 into Q nu 2 into Q nu 3 into. So 1, 2, 3 are basically denotes the modes of vibration. 1 is the first nodes of vibration, 2 is the second nodes of, 3 is the third nodes of vibration. K is the basically K normal modes of vibration. This is a V actually. QVK is a kth normal mode of vibration. So now, okay. So that means, let's suppose there's a molecule. Let's suppose a molecule, uh, molecule molecule is 5 atomic. Okay, the 5 atom is there. So that means uh, its normal modes, the number of the normal modes would be, and let's suppose the molecule is non-linear, 5 atomic and non-linear. So that means the vibrational modes are the number of vibrational modes would be 3 into 5 minus 6, 15 minus 6, 9, right? 9 modes of vibration would be there. So that means the QV would be QV1, QV2, QV3, the way up to QV9, up to the ninth modes of vibration. The all their multiplication results into the total vibrational partition function of that particular molecule. Now, one more thing, that each vibration of each normal modes of vibration can be related to a different frequency. Okay, that means their partition function definitely be different. Okay. Now we will now consider the vibrational energy levels, and from there we will be trying to get a equation for the vibrational energy levels, and from there we will be trying to get the expression of the partition function for the vibrational case. Okay, so what we'll do first is we write the vibration. So first we'll write the vibration energy levels. Okay, so for that, in order to write the vibrational energy levels, we are simply approximating those energy levels as harmonic oscillator. So there might be some anharmonic terms are there in the energy levels of energy levels of vibrational states, but for the time being, for the simplifications, we only consider the energy levels of a harmonic oscillator. Okay, so the vibrational energy levels are given by h nu equal to nu plus half hc nu bar. Okay, when nu has value 0, 1, 2. Now the issue with this to deal with this energy level, that it doesn't, like at nu equal to 0 the energy level is not becoming 0, so that might pose a problem when we are solving the energy, when we want to get the mathematical formulation to get the expression of the vibrational partition function. Okay, so to avoid that, what we can do, we can uh, include the 0 point energy level into the expression of the energy. Okay, so the modified energy levels would be looks like this: h equal to nu hc nu tilde. Okay, so nu tilde, this is also nu tilde. Nu tilde is basically the frequency, and this nu is basically the energy level. So now now by now in hand with the energy vibration energy levels, now we can easily write the QV. Okay, QV is simply the summation over V into e to the power beta VHC nu tilde. Sorry, these are all nu, not V. This is the vibrational partition function expression. There is, in the vibrational energy levels, there are no degeneracy involved. So the degeneracy factor we are taking at equal to 1. So now we can write this thing QV as summation over nu e to the power minus beta HC nu tilde to the power nu. Now the summation is over nu. That means nu will be starting from 0, 1 to like this. So summation start nu equal to 0 becomes that whole thing equal to 1, then to the power minus beta HC nu tilde plus e to the power minus 2 beta HC nu tilde plus e to the power 3 beta HC nu tilde. So like that it goes on. QV. Now QV you can write, you can convert this whole series in as a infinite geometric series, right? Where the first term would be beta HC nu tilde plus e to the power minus beta HC nu tilde whole square plus e to the power beta HC nu tilde whole cube, like that it will goes on. So it will form this infinite geometric series. Now we will simply has to use the summation formula for this kind of series that will give us this compact form, this whole thing in this compact form, beta HC nu tilde, right? The expression of QV. We got the expression of the QV now. Okay. So now now got the expression of the uh, vibrational partition function. Right now what we will see, just like the previous case, in the case of the rotational partition function, we basically approximated that rotational partition function in the case when the temperature is much higher, with the reference temperature that we are termed as the vibrational temperature, the rotational temperature. So when the temperature is basically much higher than the system's temperature, basically is much higher than the rotational temperature, the reference temperature that we have basically derived for our convenience. In that case, we have approximated the rotational partition function, right, into a simple, very simple QR equal to some theta divided by the temperature, right? So for this case also, for the case of this vibrational partition function, we will check whether we can do the similar kind of treatment here also. Okay, so we'll check. Okay, so let's first check for higher temperature. Okay, higher temperature means sorry, let's start from the lower temperature. Okay, so for lower temperature means the case 1 would be the low temperature case. So for the low temperature case, the KT would be less than HC nu tilde. That means beta by HC nu tilde would be greater than equal to 1, right? So if this is the case, then QV expression we already know is 1 by 1 minus e to the power beta HC nu tilde. Now if this thing is high, very high, then this will become 1 by 1 minus something very high, 1 by, let's suppose infinite around 1 by 0. So if this is very high, so this term will become 0. So 1 by 1 it will be equal to 1. So QV is simply equal to 1 for the case where the temperature is much lower, which is basically consistent with the energy scale, as we have discussed that at low temperature this contribution from this vibrational partition function will be very nominal, which is basically reflecting here also. As you can see, for very low temperature the vibrational partition function is becoming equal to 1, right? So that means it's consistent whatever we have derived. For case 2, let's check case 2 for high temperature. So for high temperature case, so for the high temperature case, that means the KT would be greater than equal to HC nu tilde. So that means beta HC nu tilde would be smaller than 1. So which means that we have to approximate the vibrational partition function. It is 1 by 1 plus 1 by 1 minus your beta HC nu tilde. So if this is much smaller than 1, so it to the power 0. So so you have to basically what you have to do, we have to expand this thing actually. 1 minus beta HC nu bar plus some square terms are there which we can avoid because it's small, so we can avoid the higher order terms. So QV would be approximated 1 by 1 minus 1 plus beta HC nu tilde, beta HC nu tilde. So KT into HC nu tilde. The expression of the vibrational partition function is this, right? So that means that at low temperature, as we got here, so at low temperature you can see KT is less than HC nu tilde. The vibrational partition function there is basically becomes 1. That means there is no contribution, right? For high temperature, this QV is actually linearly related with the temperature in the case which is not at low temperature, right? So you can draw a diagram. Okay, how this basically looks like. Okay, so partition function QV KT by HC nu tilde looks like this. This is 1. So after it's become linear with temperature, right? So this is how it basically looks like. Okay, the vibrational partition. So low temperature, it retains its value close to 1, and if you increase the temperature, it basically increase linearly with T, right? So now, so just like the case in the rotational partition function where you have to find rotational temperature, here also you can do that, right? From the expression of QV at high temperature. So at T equal to KT equal to greater than equal to HC nu bar, the Q vibrational takes the form like this: QV equal to KT by HC nu tilde. Now here you can define a similar kind of a temperature concept, reference temperature concept, what we can name as theta v, vibrational temperature, right? Theta v, but theta v is simply nothing but hc nu bar by k. Okay. So you can make qv, you can write qv in terms of theta v as theta equal to theta v, right? Theta v is this. So this qv equal to T by theta v is only true when T is greater than theta v. Okay. The vibrational temperature. Let me call this as vibrational temperature. Vibrational temperature. Okay. This thing actually can calculatable for a particular molecule. Okay. This theta v can be calculated. Okay. So okay, so this is how we can calculate the theta v, and if the temperature is greater than theta v, then you can approximate it. You can use this approximated formula of qv T by theta v. So you can, as you got some time, problem we'll discuss in the next class. One problem. So when you solve the problem, okay, so today I'm not going to discuss any problem right now. So anyway, when you solve the problems, okay, so basically what you have to check first is what is the temperature of the system. Okay. So if the temperature T is higher than the theta v, okay, so when you this is the tricks for solving the problem. Tricks to solve problems. The tricks is in the problem itself, the T will be basically given, right? So T will be given. Now for that particular energy level nu bar, that particular frequency, which is also given in the problem, you can calculate the theta v, and T is given. So first you have to check whether T is smaller than theta v or T is greater than theta v. Right, if T is smaller than theta v, that means the temperature is lower. So in that case, you cannot use that approximated formula, right? In that case, you have to use that conventional formula, which is this. QV equal to 1 plus, you have to do the whole summation thing, 1 plus minus beta c, 1 plus 1 plus or minus 1 minus 1 minus, or in this case you will be equal to 1 by 1 minus beta by c, then tilde, right? But if T is greater than theta v, you can just simply use QV equal to T by theta v. These are the basically two formulas you can. So the main thing is, like, in a problem you have to first check what kind of temperature is mentioned. Is it higher than the vibrational temperature? It is lower than the vibrational temperature. So depending upon that, you have to basically solve the problem. So so basically, just let me rewind again whatever we have discussed on regarding the vibrational contribution. So for our n atomic molecule, as I've discussed, the vibrational modes, if it is linear, the vibrational modes are 3n minus 5, or non-linear case, the vibrational modes are 3 and minus 6. Now next, what I've discussed, that each normal modes may be related with different frequency from each other. Okay, so that's why each normal modes has its own independent contribution to the total vibrational partition function. Like here in this equation, as you can see, the total vibrational partition function denoted by QV equal to the multiplication of QV1 into QV2 into QV3. QV1 is basically the vibrational partition function responsible for the first mode, 2 is the second mode, 3 is the third mode, 3 is the kth mode. So if you multiply all these vibrational modes, you will get the total vibrational partition function for that particular molecule. So in this example, like as you can see, let's suppose a five atomic non-linear molecules is there. So the vibrational modes will be Q9, would be equal to 9, and so the total vibrational partition function QV would be simply the multiplication for the vibrational partition function for each normal mode. Okay, up to Q of QV1 to QV9, right? Next, what we have done, we have considered the vibrational energy level. So here, I have not mentioned it. So here actually we have neglected. So we exclude the enharmonicity of the energy state and approximate as harmonic oscillator. So we are considering the energy levels as a harmonic oscillator. The H nu is simply given by this formula, and after substituting for all of these cases, we will solve some problem, but that will be doing in the next class. So for today, this is it. Okay, let me just end the class.